Welcome to my talk about just switching the compiler. So I guess that's no big deal, so it should be done in like 4 or 5 minutes or so. About me, the usual slide. I work at Zucker Engineering, we're a contractor company. I've done, I think, about half a dozen, 8, 10 projects in the last 10 years. Mostly embedded, working with C++ for about 20-ish years. So before that, at other companies, I also did a couple of things with compilers. And I had to switch compilers quite often in these last years. And this will be more or less a collection of insights, war stories about these processes of switching the compilers. So what we will be talking about is reasons why you would like to switch the compiler, the steps involved, and the pitfalls that you may or may not encounter. And we will talk a bit about strategies to avoid those pitfalls. So why would we want to switch? Well, the most obvious reason when you come to a conference like this, you see some talk using some nice feature, you get back to check, okay, this is a C++ 23 feature, we are using C++ 14, C++ 17. So you go to your team and say, well, let's just upgrade our compiler to something new so we can use these nice features, right? Another reason might be you have a new target. You want to port your program to a different operating system. You may be targeting a new chip. So like these days, we even have ARM chips in normal use PCs or laptops. Or like me in the last years, are working on embedded targets. So you have different ARM chips, 32 bits, 64 bits, different sizes. And you have different compilers targeting those systems, and maybe your compiler you're using right now is not compatible to those systems. Or you want to have access to other features. You have something specific in mind, you need some specific tooling around your compilation, something in your toolchain, and your current compiler does not support that toolchain, or the toolchain you're targeting does not support your compiler. For example, we had a time where we wanted to switch to CMake to be able to have a build system that is possible to use in multiple compilers, but we had a compiler that wasn't supported by CMake. And it would have been really hard and brittle to actually take this compiler and create some CMake magic to actually support this. Or even worse, you're changing your development machines. You're no longer allowed to use Linux because of corporate reasons, or your IT department says, well, we only support Windows from now on. And suddenly you have to switch. So depending on what you switch, I would even say switching from the same compiler for targeting Windows to targeting Linux may be a switch that where you encounter some of these things that I'm going to talk about later. Or the other way around, you have a current compiler and it's just bad and you want to get rid of it. You just want to get away, nowhere, you have no idea where, but just get away from this. I had this kind of thing a couple of years back, 12 years back, where we were using a compiler where you could just flip to includes and you would run into internal compiler error. Or you would start debugging and half an hour later the debugger that was tied to the compiler and its IDE would just crash and you had to start all over again. And at some point we said, well, this is no good, we want to get away from this. And over a year later, I left the company. They were still stuck with the old compiler because we couldn't get rid of it. And I think 2 years, 3 years later, they were still stuck with at least that vendor. They had upgraded the compiler to a newer version, but they couldn't get away from this. But, well, we have all these reasons, so what I've heard quite often, well, then just switch the compiler. Or I have said the same, well, let's just upgrade to something new, GCC 5 to GCC, let's say 8 or 9 or something like that. I had a project where we were stuck with C++11 and there was like, well, C++20 is out, so let's just upgrade our compiler. How hard can it be? Cue a slide from my very first conference talk 9 years ago. You don't just switch to another compiler. There are steps involved. It can take a long time. And in most cases, because it takes a longer time, it requires you to have both compilers supported at the same time. Because you can't just go to your customers or to your project manager and say, by the way, for the next 2 or 3 months, we won't be delivering any new features, any new updates, because we are switching our compiler. It won't compile, we just switch from A to B, and in the meantime, you have no compiling project, right? So in that time, until you are able to compile everything with your new compiler, you will need to support the old one. When you are in embedded projects, you probably will continue to support these because you want to support building for your target device, but you maybe also want to run your unit tests at least on your host machine and not always connect to the target, pull the executable over and so on. So for these purposes, switching to another compiler or just adding a new compiler to your collection is more or less the same. So let's talk about those steps. First one, infrastructure setup. You will more or less need a new development environment. You need one for your old compiler, you need one for your new compiler. In most cases, just installing the new compiler on your host machine won't be enough. If you're having like, okay, we have GCC 5 and we have GCC 8, then maybe that will be enough and you can just tell your CMake or whatever your build system is, this compiler or that compiler, and you're done. But anything beyond that may involve more steps. For example, your compilers may depend on a toolchain. In that situation where I said, well, let's switch from older GCC to newer ones so we can get away from C++11. We were not building for our PC, for our host system. We were building an embedded Linux, including Yocto. And getting a newer compiler in Yocto means upgrading Yocto. And upgrading Yocto meant going to the third-party vendor that provided the hardware and tell them, well, could we have a new bot support package, please? Because the one you are providing is only compatible to the old Yocto. If you give us 1.5 million, then yes, probably. So, no deal. You will have to think about licenses. Sometimes, depending on which compiler you switch to, it's a proprietary compiler and it costs licenses. We had compilers where a license for a single person would cost like 3,000, 3,500 euros. It was a hard sell for the customer to tell them, well, we should upgrade this one and you should invest like 15,000 euros more to upgrade the compiler. There may be legal implications. We've had people where they had a legal department that was, so the whole company was not really a software development company, and the legal department did not really know what a GNU license was. They just had a look, GCC GNU license, you have to publish your source code, no. And we did invest some time in meetings to try to persuade them and send them links, but no. So no deal there. You'll want tool chains for your new compiler. Maybe the tool chain you have for your old compiler will work. Maybe you will have to replace things. So you have your build system, CMake, Make, Ninja, whatever. Maybe code formatting tools, static analysis, dynamic analysis. They may work with your new compiler or they may not. So you will have to see what works and maybe find replacements. And then the installation you make of your new compiler, toolchain, IDE, whatever, may conflict with the old one. So you can't have them both on the same system. Maybe there's some part of the toolchain that says I'm installed here, and you have a newer version of the toolchain for the new compiler, and that says I am installed at the same location, and you can't have them both. It happens. So you will want to see whether you have two machines with native installations, or whether you have a VM, have a containerized build if you can have that. In that case, containerized builds, Docker builds are my favorite because they're really portable. You can just port them to your CI, you can port them to colleagues, and it just works. But you have to invest some time and research to figure this out. So now you're done. First milestone. You can compile a minimal program, Hello World, on your computer. Great. Going on, you have a new CI environment, because it doesn't only have to run on your machine, it also has to build on your nightly builds, on your builds triggered on commits and so on. So it's pretty much the same like your local development environment, but sometimes a little more difficult, because in many cases you don't have access to the hardware. It's on some virtual machines. It's usually controlled by IT departments if you're working in a larger company. And they may not be prepared to actually do everything you tell them. Yeah, just install this, install that, and they say, whoa, 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 whoa. You have your 4 GB machine that we already gave you, so this is enough, and everything else is like a huge paperwork, and we don't want to do this. And they usually don't look very favorably on you just buying a new computer from project money and put it under someone's desk and say, well, this is on a new build node for our Jenkins. They want to control those machines. So it's at least bureaucracy. In some cases, it's just a no-go, because it takes years to get this kind of thing approved. And when you have done this, please document how to set up your build environment. Bonus points if you just have a script and you have a new joiner and you tell them, yeah, just run the script, and when you have all the accesses and the script is run through, then you're done. Because then those new joiners can start actually working, having a look at the code and try to compile your code after half a day, instead of taking a week or so, because all the steps that you documented somewhere or nowhere and someone has done some lore how to implement them. And it takes weeks to actually figure out what you actually have to do, because the last one to do this has done it 5 years ago, and things have changed since then. And also, if you have to reproduce a build from earlier, you will want to have the script to just say, okay, set up this old build environment, run this build, so we can actually try to debug where this bug that we encountered 2 years later came from. Next milestone. We can compile Hello World on everyone's machines, including CI. What about dependencies? With dependencies, I mean libraries and frameworks. Your libraries and frameworks that you're using may not be the same that you can use on your new compiler. So you will have to check that they are compatible. If you have luck, then you can just rebuild them with a new compiler and you're set. Or you have to buy binaries from closed source. So again, you have to basically convince someone to spend the money. You have to make them available for your team and for CI. So in some cases, it's okay to everybody builds them locally. In other cases, you want to set up a Nexus or something like that, where you have like a package repository and you just pull the compiled binaries from there. In the cases where the libraries that you're using are not available for your new compiler, you will have to replace them, find alternatives. Very basic example, you are switching from Windows to Linux and you're including Windows.h, and you will have to include the corresponding Linux system headers. In some cases, you have specialized libraries that are only like maintained by a single person or by a very small team, and they're only available for this single environment. Only available for Linux, for example, and you are switching to Windows, and well, you will have to find an alternative. When finding alternatives, especially if you're using larger libraries, frameworks, make sure they fit into the architecture that you have. Especially when you're working with GUI frameworks and stuff like that, that basically spans or tend to span your whole application, and they say, well, you need to have this specific kind of architecture to actually work with this. And you introduce a new library and that says, well, you have to use a completely different kind of architecture. Then at the least that is a lot of amount of work because you have to rethink your whole architecture. Or you say, well, I have to use this library for that compiler and the other library for the other compiler. And now I need two different architectures. That's not going to work. One point also, an alternative to the library you have been using for 10 years might be in the standard library by now when you compile with a new compiler. But also, there may be no actual alternative to the library. So maybe you have this niche library and you go to the maintainer and say, well, could you make this available for macOS? And they say, well, I can give you the source code and you can try to compile it for macOS, and then you will have to maintain it for macOS. It's an investment. So when you are replacing libraries, you have to decide either you make a complete replacement, meaning you replace it for all your compilers, or you are having to use different libraries depending on which compiler you are using. So for the old compiler, you compile it with this library, and for the new one with the other library. In that case, you will get things like this, conditional compilation. When I'm on Windows, I have to include the windows.h. When I'm on Linux, I have to include the other headers. And then further down in the CPP, you say, okay, when I'm on Windows, I have to call this function, and when I'm on Linux, I have to call the other function. And this goes through major parts of your code base. Similar, in your build system, you will say, well, I have to link this library, or I have to link the other library. And this goes through your build scripts. So, a few words on the conditional compilation. Try to use your own defines. If you're using like if-defined MSVC and you have a project where you actually build your libraries in the project and they're just checked in as submodules or something like that, then finding those points or trying to find those points, you will have to do extra effort to not also find all the ways where this library actually makes the compiler switch between MSVC and all the other compilers. So having these defined flags, my compiler or my project compiler, something, makes it much easier to find them. And also consider having these else branches that don't compile at all. So if you add yet another compiler, and you define it as my project compiler, I don't know, new compiler name, then you will find all these positions immediately because your preprocessor will say, well, this is an error because you didn't define this switch case for your new compiler. You can have these for your compilers, you can have the same similar set of switches for your target operating system, you can have it for 32-bit, 64-bit, all kinds of things. So to lessen that work that you have to do when using different libraries, you want to encapsulate your dependencies. You want to have, like, in most of your code base, you want to just include some encapsulation header. And in the implementation of that header, you actually do all the switch case between Windows, Linux, and whatever. And that way, most of your code base will be dependency agnostic, and your unit tests also will be dependency agnostic. You really don't want to deal with Qt in all of your code base, and then you switch away from Qt, and then you have to change all of your code base. And please, please separate your GUI code from your business logic. And that project that I talked about, where we did not manage to actually switch the compiler in more than a year, we were using Embarcadero, which was its own compiler with its own IDE, and it supported Delphi. So we were using, for historical reasons, a Delphi GUI library. And our about 130 GUI classes all contained lots of business logic. So we had to go away and basically split the business logic from the actual GUI code for 130 GUI classes on the side of implementing new features, to then switch away from the GUI. And I think in the year we managed about 4 of those classes, so I made the math and said, well, nope. So doing this after the fact can be a lengthy process, so there's the earliest day you should do this separation of your GUI stuff, whether you want to switch the compiler or not, is yesterday. So this is a general best practice to actually take these things apart, to really say, okay, these libraries are confined to where they're actually needed and not like spread out everywhere over the complete code base. So we have hit your next milestone. We have all the dependencies in place, we have our new libraries, we have our compiler, the toolchain. We are actually ready to port our project that we wanted to port to the new compiler. So let's start and compile the project. Calling the compiler probably from a build system, you don't want to call it from command line with all the include path and everything. So you will want to update your build scripts for the new compiler. You probably have done some of this for the library stuff, but now you do it for the whole project. The command line objects, the warning options, these defines that we had earlier, my project compiler GCC, my project compiler Clang, whatever. All this kind of stuff has to go into your scripts. And then you hit compile. And it probably won't compile right away. Because as portable as C++ is, there are compiler-specific extensions, and if your project is more than a few hundred lines of code, then you probably are using some of them. This one is from a current project where we had the attribute always inline. So for those of you who know inline, it's not for inlining. It's for not violating one definition rules. And if you actually really want to inline, you want to use one of these, forcing the inline. And the compiler will try its best and hopefully actually inline your function. And the attribute always inline is for GCC, the underscore force inline is for MSVC, and I think for Clang they both work. But there is no unified, standardized way to do this for all the compilers because it's non-standard and there are slightly different semantics. So there are ways when GCC can inline things and MSVC won't, and vice versa. And there are a lot of these extensions. So again, you have like these compiler-specific extensions, and you have again probably somewhere a header for your extensions where you define your macro force inline or my project force inline. And then depending on which compiler you're actually running on, you use one or the other of these two, and then you have this function where you can just say my force inline, and it will be portable for those compiler where you have this defined this macro for. A very common example is the DLL import and export when you are on Windows and you are writing a DLL, which on Linux is called a shared object. It's not exactly the same, but for all intents and purposes, it is pretty much the same. So a library that you link to at runtime. Then when you compile the library on Windows, then you have to export the symbols from the library. When you compile the clients that use the library on Windows, you have to import those symbols. And when you're on Linux, then you have to do nothing. But you basically have to go ahead and say class, so sumlib export your macro, and depending on whether you're compiling the library or compiling the rest of your program, you have to set this macro accordingly. Be aware when compiling with newer standards, especially switching to C++ 17, which has a lot of these entries where features have been removed. These features have been deprecated before, so hopefully you don't run across these anymore because you have had some time to get rid of them, especially auto pointer. But there will also be some deprecated features where you will get warnings. By the way, still unexpected down there. That's not the still unexpected from still expected that got in there in C++ 23. This still unexpected is, I think it's an exception that got thrown when you got it's a function that got executed when you got an exception that you were not expecting. So it's unexpected exception for the old exception specifications you had before C++ 17, where you could say not only like these days no except or except, this function throws or doesn't throw, you could say this function throws this list of exception. And then the compiler had to check, well, we have a new exception that is not in this list, so it had to call it still unexpected. I think it's a bit unfortunate that this name got reused for something completely different, but it's been 6 years in between, so maybe that's okay. So what I would do in this case is, yes, you switch your compiler, but for now stick to the old standard that your old compiler supports and do the switch to where you actually switch the compiler flag to the newer standard where you run into these things after everything else is solved. Next thing on compilation will be implementation-defined behavior that can bite you at compile time. I've had a look at the C++ 23 standard, and there are 4+ pages in the appendix about things that are implementation-defined. So much for portable and code. C++ is the same on every platform, every compiler. There's a list of things that depend on the implementation, depend on the compiler. Includes a lot of the standard library. Many things are like the actual type of this and that iterator or this and that other return type is implementation defined. And you will never come across those because you just say auto or you just use the type diff for that iterator type, but there are others where you can come across. For example, the way your compiler or your preprocessor finds the files to include may differ between compilers. I mean, you have to give it include paths, and depending how you give your different compilers your include paths, they may find the header that you are including either this way or the other way and find a different header. So this may trip you up. Or your code is currently using stuff that is implementation defined, for example, execution policies for parallel algorithms that are not defined by the standard because your implementation can define additional policies for these. And then your new compiler might not support those policies, so it won't compile it there. And there are enums that can be extended by implementations and stuff like that. More common is the last one. Things your code uses might have different sizes, especially. So the actual type of size T depends on your platform, 64-bit, 32-bit. If you're using size of stuff, then this will trip your compiler. If you have narrowing conversions that hasn't been a narrowing conversion on your old compiler, it might be a narrowing conversion on your new compiler, and it will fail to compile. And one thing that we learned yesterday, who was at the quiz, if you have the names from the C library compatibility headers, those that start with a C, for example, CMath was the example from yesterday, whether those are defined in the global namespace and then imported into namespace did is implementation defined. No, it's unspecified. Unspecified means it's up to your compiler, and it doesn't even have to write documentation about it. So you may or may not have apps in the global namespace. You're guaranteed to have it in the namespace did. The same for size T. But if you just use unqualified apps, your compiler may not find it. Then, of course, while compiling, we have warnings. If you have a different compiler, you will have a different set of warnings. Your compiler may warn about stuff that your old compiler did not warn about. And if you have W error on, which you hopefully have, you will get compile errors. You can turn the W error off to not get the compiler, so you will get the errors, but you can just ignore them. But this will only shift the problem to later, because in many cases those will be bugs, and you will have to find those out later. So building without warning free is the better way to go here, because you will find those locations better when you actually turn on the warnings. To prevent those situations, or many of these situations, use static analysis. Even with your old compiler, use Clang Tidy, SonarQube, whatever you have, and crank up the warnings and see what they spit out and try to fix those things even before you go to the new compiler, because in many cases they're easy to fix, and in many cases they hint at problems, and if you just make your code a bit better to not get those warnings, then you're less likely to get the warnings when your new compiler trips over them. So we have our new milestone. Your code compiles. Does it run? Well, let's see. There is this ghost of undefined behavior. Anything can happen. In a project of a decent size, odds are you have some undefined behavior somewhere in your code and you don't know it. Code with undefined behavior can just work. Maybe you have an integer overflow somewhere and it's just okay. Maybe you have different undefined behavior somewhere and it just works, and you never come across that it might be a problem because it just does what you expect it to do. You may even rely on it, but your new compiler will say, well, this is undefined behavior, I will make something different. And there are optimizers that do quite a thing to detect undefined behavior and say, well, you will never execute this function because it's undefined behavior, right? I throw it just away. And then just your function doesn't exist anymore and you were relying on it. We'll see an example later. There is implementation defined behavior that is only at runtime. For example, the values emitted by type info name, source location, how they are formatted, what the actual message of the standard exceptions are, those are implementation defined. So please don't rely on those in your logic. If you don't rely on your logic, you still may have tests that look through logs, so higher level tests that say, okay, we expect this to happen, we expect that to happen, we expect this exception message to be put into the logs. And in those cases, you will have to update your test because the message will not be the same for your new compiler. Std hash is something special that we come across like a month or two ago. So std hash takes a type for which you have defined the hashing, and it returns a size t that is deterministic and, let's say, as unique as possible. So yes, if the size t is 64 bits, and the thing you are hashing has 128 bits, then obviously there's no one-to-one mapping. You can every input map to a different output, right? So what you come to expect is std hash will emit some deterministic garbled set of bits that is converted into a size t. The garbled part is the problem, because that's an expectation that's not always true. What is a proper way to make a std hash of an int? Well, you can just garble the bits and put out something else. But MSVC is completely correct when it says, well, the std hash of int1 is 1. That's not garbled bits. The std hash of 2 is 2, because your target type is larger than the initial type, so you don't have to actually do some bit garbling, you just put out what you got in. We didn't expect that. We had like a unit test that said, well, let's make sure that this outputs something else than we got in, and the unit test failed for MSVC. Let's get to some code, finally. Implementation defined types. Half a year ago or so, I was porting some code, embedded Linux code, that had this CAN message sent to other devices in the network. So CAN is car area network, I think. It's a relatively simple protocol. And this bunch of data was just put as is, as bytes, via mem copy into a buffer and just sent over the network. And I had to rewrite the CAN network stack. So this was relatively basic Linux stuff. And then we tested everything, and all just worked except for moving the motors. And we were like, why does it try to run against the wall? What's happening here? Well, the thing is, we switched from 32-bit system to a 64-bit system. And this CAN message initially had like, don't let me lie, 11 byte. And it was supposed to be 11 bytes. So the receivers read those 11 bytes, because long on the 32-bit system is 4 bytes long. On a 64-bit system, it's 8 bytes long. So the receiver got the flags correct, the speed correct, and then interpreted the first half of the position and the second half of the position, of the x position, as the 2 positions that it was expecting, and the other 4 bytes were just gone. So instead of, in these cases, instead of using long, you can use long types like this UN16, you can use UN32, and you will always have the same size. Except those are implementation defined. Not the sizes, because the sizes are obviously there, but whether they exist is implementation defined. But then at least you will see, okay, this is not here, so we have to find another solution. And in most systems that I know of, you will have these types. So more implementation-defined types. That very old project, we had a function to get a suffix from a string. We don't have like string view and stuff like that. This was pre-C++11 when this one was written. So we tried to find the delimiter for the suffix in the string. That's a position, that's an int or an unsigned int. And then we compare this to npos. So if it's not found, then we just return an empty string. If it has been found, then we use a substring. The problem was, again, 32-bit to 64-bit. On a 64-bit system, name.find returns a size t, which is 64 bits. And if that's npos, it's FFFFFFFF, 64 bits full. The unsigned is a 32-bit value. So the unsigned then was FFFFF 32 bits, which is not the same as NPOS. So in that case, this piece of code was trying to find a substring 4 million digits into the string, which luckily did not crash, but given an exception. We don't catch the exception, but we found the exception relatively fast by debugging. But this is a kind of problems that the code has worked for years and suddenly it doesn't. Let's go to the next one. Oh, it's the same one still. So when making this code for the slides, I used CLion and I really had to go through hoops to actually get rid of all the warnings. Because the assignment to POS, they get a warning, this is a narrowing conversion, maybe. And the comparison from POS with NPOS, you will always get like, this can never be true because you're comparing 32 bits to 64 bits that is much larger than anything the 32-bit value can hold, right? So clang D, if you use it in your IDE, it will give you the squiggles, and if you have like warnings on, then you will obviously get warnings. So take your warnings seriously, use your static analysis tools and so on. And the solution in this case is very simple, use auto. Or just use braces and you will get the narrowing conversion compiler. It's also okay, but auto is a better case here. Or string size type, or size t, whatever. Use the correct types or auto. Implementation defined types. We were writing code for a small ARM chip, and we wanted to add some logging. So I wrote this function uart put s, just put something out via uart, and you can attach your debugger or your bus to it and get the prints on your screen. And just for test reasons, I wrote this simple loop, just output all the characters from 32 to 127, all the printable characters, because the first 31 are not printable. Well, this code contains a bug because the character 127 is also not printable, which I never learned until a couple of weeks ago. But whenever we started up the device, we could get like this string of characters and we will say, okay, the UART is working great. But of course, we did not always run our unit tests exclusively on the device. So we had in parallel our ARM32 GCC and I think a local clang or something like that working on the host. Whether characters are signed is implementation defined. On ARM, on all the compilers that I know, they are unsigned, so this loop just works because they can get 128 up to 255. If they are signed, then the maximum value is 127. So this loop condition is always true. So in GCC, on the host, when I started this, I was like, why do I never get to my breakpoint later in the initialization? What's happening here? And then I saw my screen in the background just scrolling up the digits and printing negative characters and whatever. And I said, yeah, that's it's signed on my machine, and so this loop never terminates. So the overflow to 107 after 127 is undefined behavior. And the endless loop also is undefined behavior. Well, in this case, it's not, as we learned yesterday, because UART put C is a side effect, and that's not undefined behavior. So I had that answer wrong yesterday. So the side effect part was like, well. But if you put the same problem a bit differently, let's count our printable ASCII characters. Why do I always get the solution? I don't know. I had the animation to put this later. So what we have here is we get the squiggles, so because character is always less than 128 on that system. And you have this function, is it printable? Then increase the printable count and then return the printable count. So this function on Clang 21 has 3 different behaviors. If is printable is defined in a different translation unit, then the compiler has to assume, well, this may or may not be undefined behavior, because if is printable just throws an exception at the 2nd or 3rd character, then this is not undefined behavior. It returns abnormally with an exception. The loop is ended. It's no endless loop. It's no overflow. So this is great. If is printable is in the same translation unit, and you just say, well, for 1 through 31 return false, for 127 return false, for the rest return true, then the compiler says this will not throw an exception, this will just go through. This is an endless loop, this is undefined behavior. You will never execute this function, right? It's undefined behavior, I can just optimize it away, just rip the whole function from the object file. And what happens then depends whether your is printable, for example, it has been defined before count printable ASCII, or whether there's something after count printable ASCII. If there's something after count printable ASCII, that function will be executed regardless of whether you actually call it somewhere else. And when I tried it out on Compiler Explorer, I got the result of 2.5 million, so that many printable ASCII characters. When count printable ASCII is the last function in your CPP file, in a translation unit, then it will just segfault. Undefined behavior, anything can happen. And this is depending on the compiler, right? On an ARM compiler, this will just do fine. So how do we prevent this kind of surprises? Fix your warnings before you switch and after you switch. Before you switch, to just be prepared to have less warnings after you switch. And crank up your compiler warnings, WAll, WExtra, pedantic, whatever you have, to actually find your stuff. I know if you use W4 on MSVC, it will give you like tons of warnings through the standard library. At least it did so a couple years ago when I tried. And but use static analysis, use your warnings that are available for you to actually find these kind of things. And if you can, something like UB sanitizer with your old compiler and your new one, because what may be UB in the new one may not be UB in the old one. So let's talk about some strategies. So I mentioned all some of the things, some of the tips already during the talk, by like use your compiler, use your static analysis and sanitizers and whatever. But generally, do your research first. Don't just say, well, how hard can it be to switch a compiler? We do this tomorrow. Find out whether your toolchain and compiler are available, whether you are allowed to install them, whether they are compatible for whatever you want to use them for. Think about those libraries you're using. Are they compatible? Do we have to find new libraries? Do we have to maybe test around a bit with them that they actually do what we need from them? If you can, find out the language extensions. For example, grep for the underscore attribute and something like that in your code. Double underscores in a code usually mean you are using something compiler specific. That may be compiler intrinsics to just say, well, just do some bit swapping here, the function that is not standardized, or attributes, this kind of thing. If you do these kind of plans, if needed, contact your IT and legal departments. It's better to just tell them and say, we want to do this, this is a license, and we want to install these kind of things, and they say, why are you contacting us, just go ahead, than doing this, and then half a year later, we see you have done something like that, you have to roll this back as soon as possible, because you can't do this. So, better to be safe than sorry. Make a plan. Not just install, hit compile, and we are done. This won't work, as we have seen. So make a roadmap, which steps you are going to take, where you are expecting pitfalls. Probably if you just go from MSVC 2019 to 2022 or something like that, the problems won't be that bad. If you're completely switching from one compiler to a different vendor, to a different platform and stuff like that, be prepared for everything and better plan some more time to do the thing. And plan your encapsulation of libraries before, because doing this all during switch and after the switch is more work. Document the infrastructure setup that we said. Compile and run your unit test first, because those tend to be more separate from all these dependencies and stuff like that, and it's easier to fix things that pop up in the unit test and then go to integration test, larger test, to the full system. So that's it for the talk. Are there questions, are there comments? Thank you. All right. Then thanks for joining, and see you.